In this example, we want to find the eigenvalues of this matrix A, find the eigenspace corresponding to each eigenvalue, and then diagonalize A if possible. So first, to find the eigenvalues, we're going to solve the characteristic equation, the determinant of A minus lambda I equals 0. So we subtract a lambda from each of the diagonal elements of A. Compute the determinant using the formula for the determinant of a 2 by 2. And I'm going to skip a little bit of that algebra there and just write down the quadratic equation that we'll get. So we have lambda squared minus lambda minus 12 equals 0. Then we can factor that, say lambda minus 4 times lambda plus 3 equals 0. So we'll say lambda 1 equals 4 and lambda 2 equals minus 3. So that's part A. There's our eigenvalues. All right, now for each eigenvalue, we need to find the corresponding eigenspace. So let's start with lambda 1, which is 4. And to find the eigenspace, we solve the equation A minus lambda I quantity times x equals 0. So we form this matrix A minus lambda I simply by subtracting 4, in this case, from each of the diagonal elements of A. So we'll get 2 minus 4, 5, 2, and minus 1, minus 4. So minus 2, 5, 2 minus 5. Row reduce that, and we get 1 minus 1, 0, 0, which implies x1 minus x2 equals 0. So x1 equals x2, and then we can say x equals x1, x2. x1 is just x2, so that's x2, x2. So I've got x2 times the vector 1, 1, and then the eigenspace corresponding to lambda 1 equals 4 is the span of the set containing the vector 1, 1. And then for lambda 2, we do the same thing. We solve A minus lambda I times x equals 0 by subtracting a negative 3. So we'll add 3 to each of our diagonals. So we get 5, 5, 2, 2. And that will row reduce to 1, 2/5, 0, 0. So we have x1 plus 2/5 x2 equals 0, or x1 is minus 2/5 x2. So we get x equals x1, x2. x1 is minus 2/5 x2. x2 is free. So let's factor out 1/5 x2, and then we'll have minus 2 and 5. So the eigenspace corresponding to lambda 2 equals minus 3 is the span of the set containing the vector minus 2, 5. So that gives us the eigenspaces. The eigenvalues and the eigenspaces. So the last thing we have to do is to diagonalize A. So if we look at the eigenvalues and the eigenvectors, the corresponding basis vectors for each eigenspace, we know we can diagonalize A because the eigenvalues are distinct. We have a theorem that tells us that A is diagonalizable if the eigenvalues are distinct. So we can do it, and the way we do it is we factor A as P, D, P inverse, where P is a matrix whose columns are the basis vectors for the eigenspaces, and D is a diagonal matrix whose diagonal entries are the corresponding eigenvalues. When you diagonalize a matrix, it's sufficient just to give P and D.